Okay, so now we are ready to start looking at module number 7, which is going to deal with the subject of friction. So if we go into our learning plan for module 7, you're going to notice here that we have some guided notes. I have mine underneath here, and we're going to be working out of chapter 4 in our ebook in the McGraw-Hill. Okay, so back into our regular textbook, and we're going to be talking about friction. Okay, so I already have mine printed out underneath. So what I'm going to do is I am going to go underneath our camera, and I have my guided notes, but I also have the chapter here as well. So as we look at the beginning of of this section, it actually starts on page 202, which is the tail end of chapter 4 in our McGraw-Hill book. Okay, so it's not the complete chapter 4, but it's the very tail end. So friction forces. So friction is going to be a force that occurs naturally when two surfaces move relative to one another. So we want to put in here the word friction. Okay, we have all, like encountered friction, dealt with friction, heard of friction. You guys have had physics, so friction is a familiar term to you. It's also usually the reason for losses that we see in systems as they work together as well. Many times friction is something we want to try to avoid because it creates heat. But many times, or in a very strategic times, we want to have friction is our friend. So for instance, when we're driving down the road and we want to make sure that we're driving and we're staying on the road, we want to have as much friction between our wheels and the road surface as possible. So in that case, we want to have friction as a high value. But in cases where we have parts that are moving relative to one another, things can heat up, and sometimes heat can cause issues with wear or expansion, and all of a sudden things aren't going to work the way that they're intended to. So it can cause problems. Okay, so sometimes we like friction, sometimes we don't like it. Now, when we have two surfaces that are in contact that are unlubricated, it's called dry friction. Dry friction. Okay, and that's going to be the type of that's going to be the type of friction that we're going to be dealing with here in this chapter. Okay, we aren't going to be dealing with lubrications and such and trying to minimize it. We're just going to be dealing with when we have it available or when it's there, how does it affect the forces that are acting on bodies. Okay, so we are going to look at figure 411. And we're going to talk about the laws of dry friction. Okay, the laws of dry friction. So on page 203, you're going to notice that we have a couple illustrations here, and we're going to look through all three of these. So first and foremost, when we have a block that's just sitting on a surface, okay, we have two forces that are present at this moment in time. We've got the weight of the block that's going down, and we've got what we call the normal or support force that is keeping it in place here. So when it's on a horizontal surface, that normal force will always be perpendicular to the surface that it's riding on. And in this case, you'll notice that our normal force, knowing the statics that we do, is going to be equal to the weight of that block going down. Okay. Now, if we start pushing it though horizontally, as we see here, so this force P starts pushing on it in this direction, we're going to find that there is going to be an opposition to that. Okay. And that opposition is going to be these two surfaces, the surface of the block on the surface that it's riding on. There is going to be resistance. And that resistance is what we call friction or a friction force. Okay. Now, there is a zone as we push on this block where it's not going to move. Okay. And we're going to notice that it's right in this area right here. So let's look at this graph that's created. The horizontal axis of this graph is force P. So the pushing force, if you would. And then the vertical axis is going to be F, capital F. That's the friction force. Okay, that's the friction force. Now, something to note here is this angle right here is 45 degrees. It's 45 degrees because right up until this dotted line right here, you'll notice on the left-hand side, it says equilibrium, but what it means is we're not moving, Okay, you'll notice that the line is pointed at, and it's called impending motion. So it's right before it's actually going to happen. All right, and what we have is, as we push on this, this is pushing back at the same amount. So for instance, if I'm right here and I'm not moving yet, this is my friction force when that pushing force is that amount. So let's say it's 1 pound. Okay, it's starting out at 1 pound. And if I push on it with P, and it doesn't move, that means that my friction force is pulling with or pushing back with the very same amount. Some of the forces in the X have to equal 0. So 1 pound this way has to be 1 pound that way, not moving yet. Let's say I increase that to 2 pounds and I still am not moving. So this is 2 pounds. This is 2 pounds. Okay. So I'm pushing 2 pounds. It's pushing back with 2 pounds. I haven't moved yet. So this is not moving. Okay. This is stationary. This is static. Okay. A static state. Now, this highest value is called the maximum friction force, the maximum friction force. And based on what I've got here, I'm going to say 2.5 pounds. Okay. Now, I'm not quite moving. I'm almost moving, but it's almost going to like kind of go over that hump and it's going to start going. So the maximum friction force and that pushing force, I'm still not moving, is going to be 2.5. But when I get just over that, I'm going to start moving. Okay, I'm going to start moving. So anything beyond that, in our case, my made up number of 2.5, that maximum friction force, that means that this is going to push back with 2.5. This is going to push with 2.5. I'm just on the verge of moving. And anything over 2.5, I'm now going to break away and I'm going to start moving. Okay, so when I go to 3 pounds, now I'm going to be moving forward. Okay. All right. So it is important that we know in friction problems, am I on the static side or am I on what we call the kinetic side or the motion side? Okay. And by calculating our maximum friction force, that's going to be the determiner. So if my value is less than the friction force, that means that I'm in a static mode. I am not moving. If I am more than that maximum friction force, now I'm moving and I'm in a kinetic mode. Okay. So this side is static. This side is kinetic. Okay. Static and kinetic. Now, what determines if we are moving or not, or how much friction there is going to be the two surfaces that are together. Okay. So rougher surfaces are going to have the tendency to want to not move past each other. Okay. So they are going to have what we say a higher maximum friction force. For surfaces that are more smooth are going to have a lower maximum friction force. And that has to do with something we call the coefficient of friction. The coefficient of friction. Now, there are 2 values of coefficient of friction for every set of materials that rub together, okay, or that move relative to one another. And the first one that we're going to look at is going to be the static friction, coefficient of friction. And the second one is going to be the kinetic, okay? Now, I'm going to go back up over here. The static coefficient of friction is what we use to calculate the maximum friction force, because remember, motion is impending. It is not occurring yet. It's impending. It's right before. So we use the static friction coefficient to calculate that maximum. And then any of these values down here, if we need to know what the friction forces we're using, anything on the left-hand side here, we're using the static coefficient. If we are moving, you're going to notice that we're going to drop down a little bit, and all of a sudden, our friction force, kinetic, is going to remain the same, meaning I can continue to push on this, and those surfaces can only push back with so much. So it's no longer going to be, a relationship that's going to go up. My kinetic force, my kinetic friction force is actually going to be a little bit less than that maximum friction force. Okay, and we'll talk about that in just a bit. But that means that this is the friction force that occurs when I'm actually moving. Okay, and that's going to be a different value. So if I turn over my sheet of paper here, I now have a kinetic coefficient, okay, for my friction. So what I want you to do is let's fill in some stuff now that we've learned some things and catch ourselves up in our guided notes here. So friction, static friction is equal to, or it means that we're not moving. We are not moving when we are in a static friction mode. Okay. When in the static friction zone, the friction force is equal to the applied load. So if we go back over here, that was that 45-degree angle. Okay. So if my pushing force was 1 and I'm not moving, that means that my friction force is 1. Okay. Those are equal to each other. Same thing here. If my pushing force is 2, my friction force is 2. In this zone right here, 45-degree angle. Okay. Linear relationship. And then the direction of the static friction force will always be opposite the direction of impending motion, meaning, as we saw earlier, we had the P pushing to the right on that block. That means that the opposing force, the friction force, has to go in the opposite direction. So impending motion is going with the pushing force, and my friction force will always be opposite to that. It's going to be opposing it. Okay. Now, when we're in the kinetic friction zone, kinetic friction means that we are moving. We have, like, gotten it going. It's moving along now. Kinetic friction force, Fk, is less than the maximum static friction force. We see that on our chart. So here's the maximum friction force up here. It drops off a little bit, and then that friction force remains exactly the same all the way through, because now it can only push back with as much as resistance that it has between the two. Now, let's talk about why it's less. So, do you ever have that feeling where it almost feels like it's harder to get it going than once you have it going? Okay, so if I'm pushing on something and I'm trying to get, for instance, a crate going on a flat surface, a box like we see here, it's almost like I get over that hump of, okay, I've got it going, and then it's easier to push as I go along. There's 2 things happening. Number 1, we have inertia working with us. Now that we have something going, we set it in motion, and it wants to remain in motion, right? So, so we have that momentum, that mass that's working in our favor. But what's also happening is, in this state right here, those forces, those surfaces were pushing up against each other, and they had high and low points on them, roughness, okay, on each one of those surfaces. As we got this going, what we did was we smoothed out each side of that surface. So we're creating a wear that's happening. So we're wearing away each one of those surfaces. It becomes a little bit more smooth, and as we're going, we're continuing to work that. So the coefficient of kinetic friction will always be less than what the static friction was. Okay, always. All right. So the direction also of the kinetic friction will also be opposite the direction of motion. Okay, so if we're pushing to the right, that means that our kinetic friction force will also push to the left. Okay. All right. Questions here? So then at the top of the next page, what I want you to do is, let's write down those equations for static friction, for the maximum friction force, and then also for the kinetic friction. So this is found on the bottom of page 302. It's equation 4.8. So maximum friction force, it's going to be capital F sub M is equal to, the symbol for friction, the coefficient of friction is mu. Okay, it's just like that. And then we put an S on the side of it for the static coefficient of friction for those 2 materials that are in combination with each other. And then it's going to be multiplied by the normal force, Okay. Now, very similarly, the kinetic friction force, capital F sub K, is going to be equal to mu K. So the kinetic coefficient of friction for the materials times the normal force. Okay, the normal force. Now let's back up and let's look back at figure 411. Now, in this middle illustration here, we see all of these elements, okay? Kind of tip this up a little bit. There's a little bit of a shine. So normal force right here. The normal force is always going to be the force that's perpendicular to, in this case, the surface that that block is riding on. The surface that the block is riding on. So we have to look at all the forces that are coming down. So all the forces that are coming down, or the only force that's coming down here, is the weight. So when we have this block just sitting on the surface, even if it's being pushed vertically, the normal force is going to be equal to the weight of that block. Okay. Now the normal force is what we determine the friction force with. So we multiply that normal force times the coefficient of friction. Okay. So our normal force times the coefficient of friction is going to be the maximum friction force. So if we take this example and we think about the winter, and when we're driving our cars on icy or snowy roads, okay? Now it's important to have good tread because we want to increase the amount of friction as much as possible, and tread helps us, right? Tread on our tires. But more importantly, what increases this friction force is going to be whatever that normal force is. And when we talk about, vehicles, the more weight that we can actually put down will increase our normal force, right? The weight of our vehicle down on that surface, which is the road, it'll increase that normal force, which will increase our friction force, okay? So even if we don't have the best tread, if we've got a heavier vehicle, that's going to be very helpful for us, okay? Lighter vehicles don't do as well in snow for that reason, okay? Also, believe it or not, the width of your tires makes a big difference. I have I had for many years, a Ford Fusion, and I had the Ford Fusion and I had the wider, sportier tires. That thing, it had a nice V6 in it, but it was the worst in snow. And it was front wheel drive. It had a V6, so it was heavy in the front. I thought, oh, this should be good. But unfortunately, it had wide tires. And it was not good in the snow at all. And I remember I really struggled when there was any type of snow to try to get going. But then if you have an SUV, I mean, the four-wheel drive helps for sure, but when you have a heavier vehicle, or if you put some weight in your vehicle, that is going to be helpful for the friction force that we want to increase so that we stay on the road. Okay. So just kind of relating it back to something that we all are familiar with. Now, coefficient of friction. Definition. How would you explain the coefficient of friction? Okay. And what I want you to do is go ahead right now, if you wanted to, use your phones and in the chat or verbally come up with a definition that we could write down for coefficient of friction. I don't even know if there's one really in the chapter. I don't think it really does. It doesn't give you like a definitive, this is the definition of coefficient of friction. How would you describe it? Or if you look on your phones, or if you look on the internet search here on your computer or laptop, definition of coefficient of friction, and put it in the chat, or like I said, verbally say it. This is your chance. The ratio between the force necessary to move one surface horizontally over another. Yeah, I think that could be good. Anybody else have one? Let's kind of see what else we got. The pressure between two surfaces. Pressure between two surfaces. Well, the pressure between two surfaces could be when it's just sitting horizontally, right? So if I look at the pressure between two surfaces, I could look here and be like, all right, what is it? But if I'm not pushing on it, I'm not getting at any friction, right? So it would have to be when those surfaces are moving relative to one another. Would you agree? So the force exerted by a surface when an object moves across it. We just have to be a little careful with the word force because coefficient of friction is not a force. It's a number. It's a number. It's a ratio, I think is a really good number, a good way to say it. A factor that relates the gravitational force of an object to a horizontal force. Something to do with sines and cosines or tangents you might find in a little bit. Yeah. What else? What else? Others. We're all looking it up right now. We're all looking it up right now. Yeah, go ahead and you can use ChatGPT. What does it say? Does anybody have ChatGPT on their phone or a device? What does ChatGPT say? If anybody has it. I don't have it. I don't trust it. I want to hear from a couple more people. Even if you do the Wikipedia. Oh, here we go. Look at Christian did it. This is what ChatGPT says. The coefficient of friction is a measure of the relative ease with which two surfaces slide past each other. I like that. It's kind of easy to relate to, right? It quantifies the amount of resistance encountered when one surface moves over the other. It's typically denoted as mu. Yep. It is dimensionless. Yes, it is a coefficient of friction, depends on various factors, including the nature of the materials, the roughness. It's an important concept in physics and engineering, especially in fields such as mechanics, materials, civil engineering, where understanding frictional forces is critical to designing and analyzing systems and structures. Awesome. Yes, absolutely. So that's a really good definition and very complete. So thank you for looking that up. Anybody have anything else to add? Okay. Yeah, the coefficient of friction is a measure of the relative ease at which two surfaces are going to slide past each other. Let's look at a chart on page 204. On page 204. I'm going to leave that one in the chat box there for you guys to look at if you want to. So you're going to notice here that we have a chart in the middle of the page on page 204, and it gives us a chart on materials that are in contact with one another and what their values, approximate values of the coefficient of static friction or dry surfaces. Okay. Oh, Tanner got another one too. Explaining it to a child. I love it. Okay. Imagine you have two toys like cars and you try to push them along. The coefficient of friction is like how sticky or slippery the floor is. Yeah. If the floor is sticky, it's harder to slide. But if the floor is slippery, it's easier to slide. Awesome. Yes. So the coefficient of friction tells how easy or hard to slide things against each other. Great. I like that you added that, Tanner. Thank you. And kind of using that as a jumping off point, notice something about these numbers, okay? As we look, and you can kind of see it more in the high and the low of the range. That's perfect. But as we start at the top here, we have surfaces metal on metal. Okay, now that can range, greatly because it all depends on what those surfaces of the metals are like. So if it's machined surfaces where they're flat, we're going to have a low coefficient of friction. So when something is easy to move past each other relative to one another, that coefficient of friction is low. The higher the value, the harder or the stickier the surface is going to be. So as we move down here to the bottom, where it's rubber on concrete, so these are our tires on the road, you're going to notice that our values become higher. Now, 1 is the maximum value on a coefficient of friction that we can have. So the closer to 1 that we have for rubber on concrete means that we've got good friction going on. The lower the values, that means that we're going to have those more slippery surfaces, okay? So, like I said earlier, depending on the situation you're in, sometimes we want to minimize friction because friction, no doubtedly, is always going to involve heat. When we have those two surfaces rubbing up against each other or working against each other, we're going to have heat that's going to be that's going to occur. Sometimes heat is desirable, like when we are cold and we're moving our hands together to get that friction so that we can feel that heat. But other times, and especially when we're looking at machines working, we want to minimize the heat because that's a loss in our system, right? And it also can cause problems when we're looking at materials expanding or contracting and they're not doing it at the proper rate, and they can create wear a lot quicker and things can fail. So so sometimes coefficients or sometimes friction is our friend, sometimes it's not, but these are going to be things that we need to know. Whatever materials we're working with, what is that coefficient? Okay, what is that coefficient? What is that relative slipperiness or that stickiness that we have? So I'm going to have you put in your sheet. I'm not going to give you a definition, but I want you to put one in here that you feel makes sense to you. Okay, I want that to be a definition that you pick based on, you know, your little bit of investigating that we did here. Or if you found one of these explanations, which I thought were really good, ChatGPT did a great job. So did everybody else kind of chiming in, but then make something that you feel makes sense to you, like what coefficient of friction means to you. Okay. And we looked at table 4.1. So the last thing that we're going to look at is angle of friction. Angle of friction. Okay. As we look, angle of friction is going to be on our next page. Okay. Angle of friction, starting at the top of page 205. Okay, 205. So as we know, when we look at friction, the friction force and how it's going to relate to the normal force, it's always going to be perpendicular to that normal force. It's going to always be perpendicular to the normal force because, and I'm going to go to here, because our normal force will always be perpendicular to the surface it's riding on. So our friction force, probably show this. I think it was maybe on the previous page. Hold on. Yeah, I like this one better. So we will always have our friction force will always be perpendicular to that normal force. So our normal force is going to be perpendicular to the surface it's riding on. Our friction force is going to be opposite the direction of impending motion, but it will always be perpendicular to the normal force. So whether we're in a kinetic mode moving, or if we're in a static mode, it will always, always, always be perpendicular to that normal surface in the opposite direction of impending motion. Always. Okay. Now, with that, okay, what that means is, let me see here. And I'm going to actually draw the diagram. Oh, here it is. Okay. So if we know that we have a surface, okay, and we have some sort of a something on there, we have our weight coming down and we have our normal force perpendicular to that surface. Our friction force, and we'll show an arrow here, P, our friction force is going to be perpendicular to that. Okay, so maximum friction force or the friction force. Now, if we want to determine what our coefficient of friction is, okay, we are going to find that there is a resultant due to this. Okay, there is a resultant. Okay, and that resultant is going to have an angle. And that angle right there is called phi. And that tangent of that angle is going to be equal to our coefficient of friction. Right there. Okay. So if we look at, I think it's this one right here. Hope I did that. I thought it was the opposite. Shoot, it's not. It's this angle here. I'm sorry. It's the normal divided by the friction force, not the friction force divided by, I had it in the opposite direction. So phi is right here. It's going to be where the resultant makes the angle width. Okay. Oh, I did that wrong again. This one, it's this one. Why is this one? Side opposite over. So if you wanted to calculate what your coefficient of friction is, see, go down here. It's gonna be the numeric value of the tangent of the angle that is going to be the side opposite, which is the friction force divided by the normal force. So it's this angle right here. I'm so sorry. It's the smaller over the larger, smaller over the larger. That's going to be our phi. And that is the numeric value of the coefficient of friction. Okay. Now, we aren't going to be using that necessarily in our problems, but if you're wondering what your coefficient of friction is, by experiment, you can figure it out using the tangent of that angle. Okay. So we are ready to start looking at some examples. Okay. So let me get my papers out of the way here. And now we're going to be looking at our first problem. Okay. Now, the first problem that I have is this is one that I'm kind of, I did like a little, if you would, a little case study. Okay. So practice problem number 1. We have a 600-pound block and it rests on a horizontal surface. And what we want to do is we want to determine the friction force if the applied load is equal to first 100, then 200, then 300 pounds. Okay. Now, they're giving us two values of coefficients of friction. The first one is the static coefficient of friction for these two surfaces that are riding together. And then the second one is kinetic. Okay. So let's first start out by drawing our surface with our 600-pound block. Okay. So this is going to be our surface, right? Our 600-pound block is going to have a weight going straight down. Okay. 600 pounds. And it's going to be, if you would, we're going to assume that it's going to be pushed in a direction to the right. Okay. They want us to determine the friction force if the applied load is equal to 100 pounds. Okay. So this is 100 pounds or 200 pounds and 300 pounds. Okay. So we're going to look at it in each one of those situations. Now, as we know, we're going to draw our little diagram right here. This is horizontal surface, or the horizontal axis is going to be our P. Our vertical axis is going to be our friction force. And we know that our maximum friction force is going to be at the top here. Okay. And we know also that that line is the impending motion, meaning anything over on this side is static. Anything over on this side is kinetic, right? We're moving over on this side. We're not moving over here. So that means that our coefficient of static friction applies on this side and our coefficient of kinetic friction applies on this side. Now, to determine the maximum friction force, we know that that is equal to the coefficient of static friction times the normal force, Now, we have a pushing force of 100, we have a pushing force of 200, and we have a pushing force of 300. What we need to know is, what is the maximum friction force? So we know if we're 100, are we on the static side or the kinetic side? If we're 200, are we on the static side or the kinetic side? If we're 300, are we on the static side or the kinetic side? Because then our friction force is going to be using either the static coefficient or the kinetic coefficient. Okay. So first things first, we need to finish our free body diagram here. So our normal force is going to be perpendicular to the surface that that block is riding on. And our friction force, capital F, is going to be perpendicular to that normal force, opposite the direction of impending motion. Okay. So as we look here, we can sum our forces in the y direction equal to 0, because we know it's an equilibrium, to determine what our normal force is. So we have a negative 600 pounds plus n is equal to 0. So we're going to move that 600 to the other side. The normal force is going to be equal to 600 pounds. Okay, so this is equal to 600 pounds. So we know that value. Now, knowing that normal force, we can determine the maximum friction force. Okay, maximum friction force. That's going to be our impending motion line. So we'll know if anything's less than that, it's not moving. If anything is more than that, it's moving. So now we're going to say, okay, maximum friction force is going to be equal to the static friction coefficient times the normal force. We know the static coefficient is going to be equal to 0.4 for this problem. And we know that our normal force, I don't know if I can turn this off. I'm sorry, I just got an alert on my phone for a silver alert, an emergency. So, okay. I just had to try to turn it off. Okay. You guys maybe didn't get it because it's probably not in your area. This was in Brown Deer. So 0.4 times 600, my maximum friction force then. 0.4 times 600. What do you guys get?
240.
240 pounds. Yeah. Okay. So what that means is our value up here is 240 pounds. Okay. Anything on this side then, okay, and this is 240 pounds. So once we're at 240 pounds, we're just on the verge of moving. Okay. We haven't started moving yet because remember, we used our static coefficient for this one. So now anything below 240 means that we're not moving. So we're going to calculate our friction force for 100 using our static coefficient. For 200 will be our static coefficient. But now, because 300 is over the 240, we're going to use the kinetic coefficient. Okay? So we first had to determine what our maximum friction force is. We needed our normal force. Now we can actually figure out what the friction force is, what this force is when we are in each one of these conditions. Okay, so our P is going to be equal to 100, then 200, then 300. So for part A then, okay, our friction force is going to be equal to our, is going to be equal to, let me think how I want to write this. Our friction force is going to be equal to our P because we are on the static side. I'm going to try to make this is going to be the static side. So in part, I guess this would be part A, our friction force is equal to 100 pounds, right? So if we're here, like here's our 100 pounds of our pushing force, our friction force has to be that same value coming back because we're not moving. So our friction force has to be equal to our pushing force when we're in the static area. Then since 200 is less than impending motion, part B, our friction force is going to also be equal to P. Again, static. So our F is going to be equal to 200 pounds for part B. Does that make sense to everybody? So here too, here's our 200. So 200 applied down here. 200 is going to be our friction force because we're not moving yet. So this is opposing. We're still not moving. But now we have 300 and now we're on this side of things, right? So at 300 pound pushing force, our kinetic force, our friction force here is going to be equal to our kinetic times our normal. So this one we have to calculate using the 0.3. Okay. So for part C then, our F is going to be equal to our kinetic coefficient times the normal force. Okay, it has nothing to do with the friction force. It has just to do with these two surfaces that are in contact with one another, and that the maximum friction that we're going to get is this amount here. So this is going to be 0.3 times 600. Okay, so now that means that that's going to be, our friction force is going to be 0.3 times 600. So it should be 180 pounds. Okay. 180 pounds. So when I'm pushing with 300 this way, it's only pushing back with 180. So we're gonna have more force going in to the right. So it's gonna be moving, right? It's gonna be moving. Is it accelerating or not? That's a physics question. Am I accelerating? If I have 300 going in to the right and I only have 180 going to the left, am I accelerating? Gotta know, I know. Oh. Anyone else? James says yes. I see a yes, a yes. 2 no's, 2 yeses. Oh my gosh, we're tied. We're tied. It should be, because otherwise it would be equal force system. Yes. Constant velocity. So yes, we can be moving. So let's say we're right here at that impending motion and we've just broken through, okay? And then we go down a little bit and we are at 100, well, it would be a little bit lower than that. We were at 180, right? And our kinetic, our friction force when we are moving is 180 going in the opposite direction. When we hit that 180 mark, even because remember, we have to kind of break over the system. It's a little bit higher as we see here, and we get down, and now we're moving 180. If we would have 180 and 180 coming back, now we have constant velocity because we don't have a net force. Whenever we have more force going in one direction than the other coming back, we would be accelerating. So at that 300-pound mark, yes, we would be accelerating because we have a net force that is occurring. Okay. Yes, the kinetic or the friction force is less than the pushing force. Correct. Yes. Yeah. When it's equal, so at that 180 mark, when it's equal, then we're at a constant velocity. So we're still moving, but we're now in dynamic equilibrium. We call that. Static equilibrium is this side. Okay, we're not moving. So good. Does that make sense to everybody? I'm having a hard time wrapping my head around the fact that the 300 pounds has less friction than the 200. I know. But it's because of the side. So Chris, I'm glad that you brought that up. Remember, right here, this is impending motion. If I go back to my illustration here, all right, impending motion is here. This is my like breakaway point. All right. So on this side over here, it took me, for instance, we had to find where that breakaway point was. It was 240 pounds, right? 240 pounds. So now when I break away, those surfaces actually push past each other. Okay. And it's easier to get going. Like it's like once they break away, now they've got momentum going with them. They're smoothing over those surfaces as they push along. Okay. So that kinetic friction coefficient is less than what the static was. Okay. And now it can only push back with that amount. Like that's it. It's not going to offer anything more. So it ramps up to the max. It comes down a little bit once we get moving. And now on this side, when we know we're on the other side of that impending motion, now the kinetic friction is the only one that's going to act. 300 pounds has less friction than the 200. Yeah. And it is because it's actually moving. It's because of this dip. It's because of that dip that's occurring. Because we haven't gotten it going yet. Think of a cap of high friction can be before it stops being as effective. Yeah. Okay. Okay, good. Anybody else have any questions? Because it is a little funky. And it's because of that little bit of difference there. And there's a couple different variables that are going on. There's also heat that's occurring too on the surfaces. So we've got heat building up. We've got those surfaces getting a little bit smoother just as they pass by each other. We've got momentum working with us. So that friction force is always going to be a little bit smaller. So it's that whole thing of, okay, I got to get this going. And it's almost harder to get it going than when we actually get it going. And that friction, that friction force plays into that as well. Okay. All right, good. Good. All right. This is going to be similar to the first problems that you have to do, except the problems that you have to do are going to be at an angle. So they're a little bit more, but it's the same concept. We have to figure out where our impending motion is occurring and then determining which side or the other that we're on. So I'll talk about that when we look at our application problems. Okay, let's look at our next problem. We'll turn the page. Okay. All right, our next problem is going to be problem 486, part A on page 216. On page 216. So we're gonna go into that head. All right, so what we're gonna do is we're gonna look at this cabinet. Okay, it's 120-pound cabinet. And what we want to determine is you're going to notice that it says that the coefficient of friction between the floor and the casters is 0.3. Okay. If H is 32 inches, determine the magnitude of force P required to move the cabinet to the right. Okay. And I'm sorry, if both casters are locked, we're just going to do part A. Okay. If both casters are locked. So it's almost like it's just sitting on the floor, flat on the surface. Okay. And we want to know, determine the magnitude of force P, you know, to move that cabinet to the right. So it's going to be basically our maximum friction force. Okay. So we are going to draw a diagram as we see it here. And we're going to simplify it a little bit. And I'm going to draw the surface that it's riding on. Here's our cabinet. Okay. I'm not going to worry about the wheels. I'm just going to show it as a flat surface. I know that it's 120 pounds. Okay. And I know that force P is 32 inches above the ground level. Okay. I know that the width here is 24. Okay, so we can put that on. And I know that this point is B. And I know that this point is A. Okay. Now, as we look here, if we want to know how much we have to push on this before, you know, it just starts going, we are going to mimic our normal force. I like putting it at the corner over here. Okay, the normal force right there. And that's going to be perpendicular. It's kind of like this ends up coming up off the floor just a little bit, and all the force is at that front corner right before it starts, for instance, tipping over. Okay. Then we know that our friction force F is going to be there. Okay. And it's going to be the maximum value of the friction force because it's going to be right before it's going to maybe tip over. Okay. Now we're given in this problem that our static friction between these two surfaces is 0.3, and we're going to show our convention. Now, you can see here that to determine that force P, the only opposing force to it is going to be our maximum friction force, right? And we know that our maximum friction force is equal to the static coefficient of friction between those two surfaces times the normal force. So what we need to do is determine what that normal force is And then we can calculate our maximum friction force will then equal our P, okay? So to determine our normal force, we're gonna sum our forces in the Y direction equal to 0. So as we can see here, we're gonna have N minus 120 equal to 0, N is equal to 120 pounds. Okay. Then our maximum friction force, do that over here, maximum friction force is going to be equal to that static coefficient times the normal force. So we know that to be 0.3 times 120 pounds. So our maximum friction force here is going to be 36 pounds. And then lastly, sum of the forces in the X. And now we've got P, right? P is equal to, or P, I'm sorry, minus 36 pounds. The maximum friction force is equal to 0. P is equal to 36 pounds. There you go. So pretty straightforward. Any questions kind of on that one? And again, just doing the part A. This is going to be something similar to what you end up doing for your homework, except in that case, you're going to know what P is, and you're going to have to actually calculate for the height. But we'll look at that when we look at application problems. Okay. All right. The last problem that we have, this is one of my favorites. I like this one. We're going to do a ladder problem. Okay, we're going to do a ladder problem. And we have a 25-pound uniform ladder that's 8 feet long. It rests up against a smooth wall. And a 175-pound person climbs up the ladder to a point, a distance L, and we'll show that in our illustration just a little bit, before that ladder starts to slip. If the coefficient of friction between the ladder and the ground is 0.4, what is the distance L that the man can go up the ladder if the angle between the ladder and the ground is 60 degrees? So let's kind of draw this out. It's got a lot of description here. There's enough information, but let's make sure we all understand what it's asking us for. Okay, so this is going to be our wall, and this is going to be the ground surface, and we are going to have our ladder something like that. Okay, and our ladder is at a 60-degree angle. I'm going to call this point B, okay, and this point A. I'm going to draw it like here-ish, okay, and this is 90 degrees. This is the smooth wall, all right, and this is going to be the ground surface then. Now, let's draw a couple other things here. It says that we have a 25-pound uniform ladder. So if we know this to be 8 feet long, that means right in the middle, uniform, okay, half and half-ish, we are going to have 25 pounds, right? Coming down. That's the weight of our ladder. So it would be like 4 feet, 4 feet, because it's an 8 foot long. Then it says that we have a 175-pound person climbs up the ladder. We're going to put them about here. I'm pretty sure it's above the center, but we'll find out. This is going to be one. Not very straight. I should be using my straight edge. I should know better than that. There we go. This is going to be 175 pounds. Okay. Now let's add some dimensions along here. So we know that our ladder is, go on a bit further. I know it's going to go into my writing, but that's okay. I know that my ladder is 8 feet long, right? I know that that total distance is 8 feet. And that I also know that up to that 25-pound uniform weight of my ladder, I know that's going to be half the distance of 8 feet. That's going to be 4 feet. Because we're taking the weight of that ladder and we're concentrating at its geometric center. And then the distance L that they're referring to, that's how far that person can go up the ladder. So we want to calculate that distance. Okay, distance L is what we're looking for in this problem. This is like what we're trying to find. Okay. Now, those are the applied loads. the weight of our ladder, and then the weight of that person. Now what we want to do is we want to put in place some other things, okay? We know that at the bottom here, there's going to be some friction, right? Friction at the ground level. Now, at this point where the ladder is, that's holding up our normal force, okay? This is going to be our normal force, perpendicular to the surface that our ladder is riding on, okay? Now, this ladder is going to want to move this way, right? So it's going to want to move that way. So the friction force is going to go in the opposite direction of motion, opposite direction of motion. And that maximum friction force, because we want to know how far they can go up right before it's going to start to slip, that maximum friction force is going to be that value there. Okay, should put our convention in here because that will come in handy, same as what we've been using. So that's what's going on down here, our friction and our normal force. Now, it told us in the problem that this is a smooth wall. It's a smooth wall. So what that means is there's no friction. So the only thing that this ladder is seeing is a reaction perpendicular to that surface. There is no friction up there. No friction up there. If there was, this would want to go down the wall and we would have then a friction force going up. But because it says a smooth wall, we're assuming no friction, and we're just going to call that B. Okay. B. So reaction at B, smooth surface. And then we've got the reaction at A, normal with a friction force. Normal with a friction force. Okay. And we want to get to what is L. All right. So let's first of all try to identify our normal and our friction and our B. These are our reactions at our supports, right? Our reactions at our supports. So if we look here, can we figure out what our normal force is using our equations of equilibrium? Yeah, right. We can sum our forces in the y direction. There's only one unknown in the y, which is our normal force, to find out what that normal force is, right? And we know that our friction for our maximum friction force is going to be the static coefficient times that normal. So once we know the normal, we'll be able to get at this because it tells us that it's a 0.4 coefficient of friction with the ground. So let's determine what our n is, okay? So sum our forces in the y. Actually, I'm gonna go down here a little bit further. Sum the forces in the y direction equal to 0, because I think I'm gonna have to add some distances here. So I want to keep that open. So I know that I have a 175 pounds, a minus 175, minus 25 pounds, and a plus normal force is equal to 0. So adding these two together, putting them on the other side, our normal force is going to be equal to 200 pounds, right? So this is equal to 200 pounds. So now if I know that, and I know my coefficient of static friction, I can calculate my maximum friction force to be 0.4 times 200 pounds, right? 0.4 times 200 pounds. So my maximum friction force here then is what? Is that 80? It is 80 pounds, okay? So we know this to be 80 pounds. We know that to be 80 pounds. Can we calculate B? Yes, we can. Oh, thank you, James. I just saw it in the chat. Yeah, we can, right? Sum our forces in the X direction and we can get B, right? So good. So let's do that. I'm going to go underneath here, sum our forces in the X equals 0. And we can say positive B going to the right minus 80, oopsie, 80, not 800. 80 for that maximum friction force is equal to 0. Our B is going to be equal to 80 pounds. Okay, so we can put that up here as well. Okay. So we know our reactions at our supports, which are B and A. Now what we want to determine is what that L is, okay? So to get our L, that's a distance. We've used some of our forces in our X, some of our forces in our Y. So now we're going to exercise our moment, okay? Some are moments. So let me grab Another piece of paper. I'm gonna kind of go over the top here. You might have to go on the next page, like turn over. That's okay. Unless you have a smaller diagram. Now, what we need to do is we got to get at L, right? So if I put my finger around A, for instance, or B for a moment, and I pull in the direction of the force, notice that this is not the perpendicular distance to A for this force. The perpendicular distance to A would be this distance. Do you see that? So what I need to do, and then the same thing here, this distance is not going to be the perpendicular distance into 4, it's going to be this distance. So we need to use our 60 degrees to find our perpendicular distances from A, okay? So what I want you to do is exactly that. I want you to calculate what those distances are, okay, down from here. So we're going to need this one. Oops. We need this one. Okay, we're gonna need this distance. We're gonna need this distance. And then once we have those, we can use the 60 degrees to find that L. Okay, we're gonna need that one. Then the other perpendicular distance we're gonna need is going to be this one from here to here, because we need to include that 80 pounds in our moment. So I'm going to call that H for height. I'll call this D1 and D2. So what I need you to do right now is to calculate H, D1, and D2. Go ahead and use your trigonometry skills, your right angle trig skills. We all should be calculating. Let me know when you get a value for H. James said he got H is equal to 6.93. That is correct. How did you do that? Did you do the sine of 60 degrees times, so the sine is the side opposite, right? Over the hypotenuse times 8 feet. Okay, should be how, I'm sure that's how you got it. So H is equal to 6.93 feet, right? 6.93 feet. Good. Okay. Right, that's one of them. How about D2? D2 is one that we can get numerically, right? Because D2 is going to be the cosine of 60. And then 4 feet is its hypotenuse, right? So D2, yep, it's going to be the cosine of 60 times 4 feet. So D2 should equal 2 feet, right? Because the cosine of 60 is 0.5. So D2 is going to be equal to 2 feet. 2 feet. Okay. And what about D1? D1's hypotenuse is L, right? And that's going to also be the cosine of 60 degrees times L. So we know exactly that. Thank you, Josh. It's going to be D1 is going to be equal to 0.5 times L. 0.5 times L. Okay. So D1 is equal to 0.5 L. All right. So now we're going to sum our moments around point A, and we should come up with a value of L. So in place of D1 here, perpendicular distance, we'll put 0.5 times L. So let's do that together. So I'm going to kind of put this underneath here. I'm going to put my finger on A. I'm going to start with B, and I'm going to rotate in the direction of that force. It's going to cause rotation. So sum my moments around point A equal to 0. So I'm going to have 80 pounds times perpendicular distance from A is the 6.93, right? 6.93 feet. And it's going to rotate in a clockwise direction, which will be negative out front. My next one is going to be I'm going to do my 175. It is going to cause rotation. So I'm going to have 175 pounds times perpendicular distance, 0.5 L, 0.5 times L. And then out front is going to be a positive value because it's going counterclockwise. Same thing for the 25. So 25 pounds, but this time that's going to be times 2 feet, right? 2 feet. And it's going to be positive out front because it's going to rotate counterclockwise. And those are all the forces causing rotation because through point A here is going to be my friction force and my normal force. Those won't be included. I set this equal to 0. So now I'm going to go and I'm going to combine what I can, push to the other side, and solve for my only unknown here is L. Okay, so go ahead and do that. So you should come up with 5.76 feet for L. 5.76 feet for L. As we look, then that means that the 175-pound person can climb 5.76 feet up. Okay, and that is the correct answer. I know that to be correct. Okay, so questions on that problem using friction. And definitely friction is something that we're looking for, that we're, you know, counting on in that case, right? All right. So that takes us to the end of, that's the last problem that we have. You would be ready to start looking at the Module 7 application problems, okay? So, so that is my lecture and my practice problems for Module number 7. I'm going to stop the recording here. Okay.